So clearly the fundamental problem with the remainder estimate is how do we find a bound for the n plus first derivative at c, because we're using this letter m in our error bound that is the maximum of the absolute value of the n plus first derivative at c on the interval xa or ax. So basically there's three things you can look at. Either your absolute value of that n plus first derivative is bounded, like sine and cosine. No matter how many derivatives of sine or cosine we do, it's always going to be sine or cosine, positive or negative. The absolute value will take care of the positive or negative. What we get is going to be less than or equal to 1. All right. You could have a situation where the n plus first derivative is increasing. For example, 2 to the x. No matter how many derivatives I do of 2 to the x, I'm going to have 2 to the x times some power of ln2, and that is going to be an increasing function. Likewise, I could have my n plus first derivative be decreasing. So, for example, e to the negative x, the derivatives are all e to the negative x, negative e to the negative x, e to the negative x, negative e to the negative x. All right, but in the absolute value, they're all just e to the negative x, which is a decreasing function. So you could have any of those situations. The derivatives doesn't have to be always increasing or decreasing, and they don't all have to be increasing or decreasing. You just have to look at that n plus first one. And if we know that what the n is for a particular problem, then we just look at the n plus first derivative and say if I got something that's increasing or decreasing on that interval that I'm interested in when I'm looking at the absolute value. All right, so that is basically the three ways we can get a handle on this. So let's apply that. So here's our next example. We're going to find the Taylor polynomial with n equals 3. By the way, this is often called the third degree Taylor polynomial, or T3. Not T4, T3, it's T sub 3. All right. This is a symbol that you really need the context to for people to interpret, but it is a common symbol. And then we're going to use that T3 for ln of x with a equals 1 to estimate the ln of 2. All right, and then we're going to ask what is the maximum error for this estimate. But first, I want you to pause this video and just get the Taylor polynomial, okay? Pause it. Do the problem. Okay, now you did the problem, and if you came back without pausing and doing the problem, go back and pause it and do it. All right, here's the result. So here's our third degree polynomial, T3, for ln of x at a equals 1. So here are all our derivatives. I wrote them over here. For some reason, I get squinching over there. Here are they evaluated at a equals 1. Here are the coefficients we get. Here are the powers we're going to put in. I went up to n equals 3, but then for n equals 4, I just got that n plus first derivative because I'm going to need it for the error term. So, but I'm not actually using that as part of the Taylor series because we're stopping at n equals 3. All right, so for our Taylor polynomial then, we just put these coefficients with these powers. Here they are. They simplify a little bit because there's a 0 and unneeded parentheses. All right, so here's the answer to the first part of the question. Write the Taylor polynomial for ln, which is the T3, which is that. All right, and then the second part of that was to use it to estimate ln of 2. So here's my estimate for ln of 2. It's 1 minus 1/2 plus 1/3. And I chose not to say what that is, although if I think about it too long, it's probably like 5/6 or something. Isn't it 5/6? I think it is. I think it's 5/6. Anyway, I'm not going to sweat that. I'm just going to leave it like that. All right, so what we need to get a handle on to use the error estimate is we need to know this magical number m, that is the maximum value of absolute value of f. So our n is 3, so our n plus 1 is going to be 4. So that's the n plus first derivative is f4 of c on c in the interval of 1 to 2. All right, so here's what I know. I know from my table up here that the fourth derivative of x, the absolute value of the fourth derivative of x is the absolute value of negative 6 over x to the fourth, and that's equal to 6 over x to the fourth. All right, so you can think about this function. This is a decreasing function. As x increases, this function gets smaller, and it's always positive. So we observe that absolute value of the fourth derivative of x is increasing on 1, 2. Therefore, since the function is decreasing, right, I have my interval 1 to 2, and I have a decreasing function. So the maximum is just going to be the left endpoint. So you're spared usually from having to do some kind of optimization problem to find this maximum. Usually we just want some kind of bound. So if I have a decreasing function, I use the left endpoint. If I have increasing, I use the right endpoint. But you do have to use absolute value when you look at that. Because if I don't have the absolute value, I would actually have a function that's increasing. It's down here. And then I would be led to use the right endpoint, which would be wrong. All right? The absolute value is, oh, I wrote the word increasing here, but that absolute value, clearly this function is decreasing on 1 to 2. Right? It's the f4 that's increasing. Absolute value of f4 is decreasing. So our maximum value is here on the left. All right, so we're going to use the left endpoint. Use the left endpoint of this interval. So our m is equal to the absolute value of the fourth derivative at 1, which, according to this equation up here, with this part, is 6 over 1 to the 4th power, which is just 6. All right, that's what my m is. So now I know that my remainder term, the absolute value of the remainder, which is the maximum error, is less than or equal to, from our Lagrange formula, m times x minus a to the n plus 1 over n plus 1 factorial. So that equals 6 times 2 minus 1 to the 4th power over 4 factorial, which is equal to 6 over 24, which is 1/4. All right, so that's my maximum error. Now we can sort of check some of these things out a little bit because it's kind of interesting. So first of all, I'm estimating ln of 2, and oh look, I got the alternating harmonic series. We already know the alternating harmonic series converges to ln of 2 from some of our earlier work. So let's see. I guess I didn't put that on here. Let's just clear everything out. So my third degree Taylor estimate of ln of 2 is 1 minus 1/2 plus 1/3. And that should be close to ln of 2. So yeah, that's 5/6, right? And then ln of 2 is 0.69. All right, so it's pretty far off. We expected that. We can have an error of 0.25 here. That's because we're only using 3 terms of the series. Of course, if you wanted an accurate ln of 2, you would use, many, many more terms, although in some of our earlier error analysis, you see that probably would only be like 7 terms, but that's still too much to write out by hand. So that's why I stuck with 3 for these, and your book sticks with 3 in the AP exam, and everybody sticks with 3. All right, so let's see what our actual error was. So if I take my estimated value and I subtract my calculator value, I get 0.14. All right, and that's clearly less than 1/4, which is 0.25. So it is correct that my error that I got is less than 1/4. So I was within 1/4 of the correct solution.